Okay, welcome back. We're going to start the coding portion, and I just posted quickly in polls and answers. Just wanted to know how everyone's doing so far. So if you can hop over and just answer, does chi-square, does the previous lecture make sense so far? One, not at all, or five, you definitely have it, all makes sense. Just so I can gauge how much we should kind of talk about some of these topics in the coding portion. So, okay, so we will talk about how we actually wrote the code for some of these. Um, so, and I see no one is a one, which is good in the polls and answers. That's very reassuring. And if you are feeling a little bit confused, that's okay. I will try to reiterate some of those concepts here again. So let's talk about how we would actually generate the code, how we would do some of this. So if you have your notebook open, please try to follow along. Okay, we are first going to import our packages. So I think you're going to find that actually the code for the chi-square test is very simple. Python will do a lot of it for you. So that's why it was important that we spend some time in the analytical portion, actually understanding what it's doing, because it will just give you a number. It will make the table for you and give you your p-value, and you can do that without actually knowing what went on behind the scenes. So that's why it's important that we talk about how you actually get that p-value, and we can definitely go over that again. So here are the packages that we're going to need for today's lesson. We will first read in our CSV, our data. So that is our Chicago crime data. And we can actually specify if we want to tell Python right off the bat what type of data or what type of data a certain column is, we can specify that here. So we can say D type, we can tell it an ID that the ID is an object and that the column beat num is also an object. Okay. And so I'll answer, there's a quick question about if a crime happens, it's many crimes. I think it would be counted in multiple. So if there was a homicide and a robbery, I think that would be counted twice. So if someone robbed you and murdered you in your home, it would be counted as, I think, a robbery in a residence and a murder in a residence. And so, yeah, the penguin will be used for t-tests. So we'll talk a little bit about how to do that as well. Okay, so yeah, we can specify the data types. So here we don't want Python to think that this is a number. It's just an ID. So we want to tell it it's an object. So that's all you can do. So that's handy. You can add that there to specify the type of data of a particular column. So we already went over this data set. What we care about is primary type and location description. So if we wanted to look at all of the different categories that we have, we can do it this way. We can just say of the primary type column, we don't want any duplicates. We just want the unique columns for the types of crime. And that will tell us, this is a really big data set. And so we want to know how many different categories are we dealing with? How many different types of crimes occurs? And you can see it's a lot of different crimes. There are a lot of different categories. And the same for the locations. Here, it doesn't even print all of them out. There are 128 of them. So we have a lot of different locations, unique locations as well. So that is what led us to, in the previous lecture, we talked about how we would want to compress some of those into wider categories. So we classified things as a residence, and we put a lot of different categories from location into residence and other. So because we have so many of these, that would make a huge table, and we had a lot of those zeros. So the way that we classified our data into those wider categories is actually by making a dictionary. So There are a couple of caveats here to pay attention to. The first thing you probably notice off the bat is this is a lot of text. What this dictionary is it's taking all of these. So here, this is the one where we are going to compress all of our locations down into particular categories. So remember we had airport and related. So we're putting all of these crime locations and we're going to call them airport and related instead of airport aircraft, airport vending establishment. All of these, they all fit under airport and related, right? They all they all happened at an airport. So we classify them all as airport. The same with hospitals and related. We had, all of these different categories, but they all kind of fit at hospitals and related. So one of the issues that you might notice is this is a lot to type out. This is, a very basic way of doing this. So it's straightforward in that we just make a dictionary to classify all 128 of our crimes into the category we want to put them in, right? That's our dictionary. We're saying if it happened at a pawn shop, call it bank and related. Currency exchange, bank and related. So you can see that this is how we got those wider categories. And this is a very simple way to do it. And so if you are unsure, you can also do this in more complicated ways, but it gets significantly more complicated above this. So a dictionary is the simplest way to do it. It's a lot of text, but if you were to start doing for loops or, trying to pick out particular words, the problem with this is it might be hard to do because you have to know what all of these are and how you want to classify them. And you would need to find things in common in the words to tell Python, put everything that has this particular word into bank and related, right? And it's kind of hard to do here because we have credit union, pawn shop, riverbank, savings and loan. Only one of those had bank in it. So a dictionary is a lot of text, but it is a way that you can get all of your categories the way that you want. And we did the same thing for our offenses. So we call these theft related if it was a burglary, a robbery, a theft, motor vehicle alert. So this is the way that we have made those other categories we talked about in the last lecture. So we made this dictionary. There's a question about if you could use Excel, possibly if you wanted to copy paste that text, or you could write it in a Word document and copy it into Jupyter Notebook. So we are going to, the next thing that we're going to do is create a new column in our data set, because now we want to put all of these into their new categories. But we don't want to alter our original data set. We just want to add on a new category that has, these new wider categories in it. So the way that we do that is pretty simple. We're going to create a new column in our data frame called offenses cat, and that is going to be our wider categories for offenses. So what we're going to do is say we want to put in that new column based off of the primary type column. We want to replace it with our dictionary. So what it's going to do is anywhere where it sees, anywhere in the primary type column where it sees crim sexual assault, it's going to replace that with sexual offenses and related and put that in the offenses category column. The same with location. It's going to look in the location description column of our data set and then replace anything there with our dictionary. So for location, if it sees pawn shop in that column, it's going to put in the new column instead bank and related. So now when we look at our data set, the output here, now we can see we have these columns, these new columns that have our wider categories that we can work with from now on. We still have our original primary type, but now we can see that it's classified slightly differently. Okay. So now that we have organized our data in the correct way, what we want to do is make that count table, that contingency table. So a contingency table is super easy to make in Python. So all you do is use the crosstab function. So to make our contingency table, which remember had those raw counts, it has here, for example, that 252, remember, was the number of crimes that were dangerous practices that happened in an airport or related. So the way we do this is we name it my contingency table. You need to name your variable. We use pandas pd.crosstab, and then the index or the rows, we need to tell it what column do we want the rows to be. And we want it to come from the offenses category column. So remember, we're pulling it from up here. That's right here. That's going to be our rows. And you can see in the output that became our rows. And then we have our columns. We want to be the locations cat. That's our new location column right here. So that's going to be our columns. So all you have to do to make this contingency table is use crosstab, tell it what the rows should be and what the columns should be, and it will do the counts for you. Okay. And crosstab is a little bit different from a pivot table. I mean, pivot table has a lot of different functions, and that's in Excel. In crosstab, it's just the counts. Crosstab is just giving you the frequencies in this case. This is just going to count for you. But you could make a pivot table with this data as well if you wanted to count. But this is just an easy function here that can give you that count data. And the benefit of using crosstab is we can also normalize it. So crosstab is really made specifically for contingency tables. And so we'll talk about normalizing now actually, and then we'll show the code for how you would use that crosstab function to then normalize your data. Because in the last lecture, remember we talked about we can normalize. So the first thing we do is make these into percentages, and then we can normalize them based off of column or row. And so just to clarify one more time, that if we did it based off of column, that would take all of the airport and related crimes and say what percentage of them were dangerous practices, what percentage was non-criminal, what percentage was other offenses. So if we did it by column, that's adding up all the airport and related and dividing it into the percentages. If we did it by row, that would be saying of all the dangerous practices, crimes that occurred, what percent happened in an airport, what percent happened in a bank. So that's what we're going to talk about here. So our crosstab, this crosstab function gives us counts by default. But if we wanted to make it into percentages, which we need to do to have our data be more clear and to do our chi-square test, is that we went ahead and we can do this normalize function. So remember, we've talked about this a lot now, that you can normalize by columns, and that means that each column will sum to 1 or 100%. And if you normalize by index or by row, that means that each row will sum to 100% or 1. So, we talked about that in the last lecture, and then, this is how we're actually going to do it. So we'll show this example. So if we wanted to make that contingency table, the same one we just looked at, but now we're going to normalize it by column. And like we talked about in the last lecture, you should look at it both ways. Normalize it by row and by column. Definitely do both of those to look at those patterns, because those heat maps can show you if maybe different patterns have arisen. So the way we do this is the crosstab function. Again, the same thing. We say, what column do we want to pull for the rows of our table? And here we're saying our offenses, we want those to be the rows. And then we say, what do we want the columns to be? We want that to be the location cat. And so that here becomes our columns. And then we want to normalize by columns. We also could have said normalize by index, but here we're saying normalize by columns. And then we want to multiply it by 100. If we don't do that, it will give us the percentage. It would say like 0.2 here instead of 20%. So this just makes it a little bit easier because you're reading the actual percentage instead of, like 0.2. So that's just to make it easier to interpret for a user. So that's why we multiply by 100. So now you can see that we have that table with the percentages. Since we normalize by column, this column will equal 100%. So now we can see that of all of the airport crimes that occurred, 49% were theft related and 14% were violent crimes. And so, yeah, you could round those as well. You could add code to round it so that you could have up to the highest number, or you could round it down. So in this case, it is hard to interpret with numbers. So this is, so the sum of the percentage by columns would be 100%. There's a question about that. So if we had summed all of these by columns, each column will equal 100%. So yeah. But really, when we look at this table, it's just a lot of numbers. That's why those heat maps are important, and we'll do that in just a little bit. So the first thing actually that we're going to do is exercise 1. So we'll talk, I know that there's a lot of questions about, oh, this is a lot of numbers, we have a lot of decimal places, but this isn't really a great way to visualize the table. This is just kind of an initial inspection to say, okay, approximately 49%, things like that. But really those heat maps are the best way to say, where do we see those differences? So for exercise 1, you're going to try the code now. So produce a contingency table in which the values are the percentage of offenses of a particular type that occurred in a particular location. Looking only at offenses of type property damage, what is the most common location where this type of offense occurred, and what is the relative frequency? So I'm going to give you a hint. Don't filter your data by just after you make your contingency table, just look at property damage. You don't need to have the table with just property damage. Does that make sense? So make a contingency table just like this one, but instead we want to have the values that are the percentage of offenses of a particular type that occurred in a location. So let's take just a minute and go ahead and try to write. It should be, another hint is the code will be very similar to what we just did for the example. Okay. I'll give you just a minute more. And then just as a reminder for our contingency tables, while you're working on the code there, that what we're looking at here, because I know we talked in the last lecture about, our actual table versus our null hypothesis table. So what we're calculating here with crosstab, just to clarify, this is our actual data. So this was pulled from our, our raw counts, the data that actually occurred. And then, when we calculated that other table, that was calculated based off of if everything was independent. And then just to reiterate, the reason why we did that was because we want to know if our actual data differs significantly from our ideal data or our independent relationship data. And I just wanted to clarify, because we won't necessarily see how that table is made. Like I said, Python will do a lot of this for you. So let's go over exercise 1. So here, it's the exact same code, except before we normalized it based off of column, and now we're normalizing it on rows or index. So here we can see instead, let's look at how this changed. So now we normalized it based off of rows. So our airport and related, the dangerous practices that occurred in airport and related were 1% of all of the dangerous practices crimes that occurred. Most of them, 1% of them happened at an airport. Most of them happened at a residence or related, right? So that's different. Here, when we looked at of all the airport crimes that happened, actually 20% of them were dangerous practices when we normalize that based off of column. So that was looking at airport and related crimes. We saw 20% of airport crimes are dangerous practices. But when we normalize it the other way, we can actually see that most of the dangerous practices, crimes, occur in a residence or residence and related. Only 1% occur at the airport. So you can see how normalizing a different way can show you different patterns. Neither of these are wrong or right. It's important, you're just looking at your data in a different way. And so that's why it's important to do this. You can see different patterns when you normalize things in a different way. And so, yeah, both of these are absolutely correct. It's just, you know, showing the percentages of things in a different way. Okay, so like we talked about before, these are a lot of numbers, and so it can be hard to pick those out. It can be difficult to say, okay, dangerous practices, we saw 39% for residents, and then you're scrolling around and we're trying to find, okay, property damage, where did most property damage? And so it can be hard to keep track of those numbers because most property damage occurred for street and related. A better way to look at this could be a heat map. So heat maps are also pretty simple to do here. All we have to do is say, use seaborne package, sns.heatmap, and then my contingency table, which was what we named. Let me go back up. Oh, sorry, it's all the way up here. We named that here, my contingency table. So we named this variable when we made this count here. So all we have to do is put in, you know, sns.heatmap, and then the name of where we gave our contingency table, what we named it, that's all we have to do. And then we can see this heat map. But I'm gonna guess, I haven't looked at the live chat yet, but I'm guessing that everyone is gonna say that this is kind of hard to see, right? This is also counterintuitive. Normally darker is higher numbers, but here we're seeing dark, it's just dark. It's hard to see the pattern actually with this color scheme. But don't worry, that is the next thing that we'll go over, is how to change the color scheme. So this is also pretty simple. You can, to make this more legible and, you know, a little bit easier to see where darker colors mean higher numbers, which is what we're used to, all you have to do is say CMAP equals reds. And then here you can click this on your own time and go over all of the different color palettes. You can do heat maps in a lot of different ways. But here, if we just put in reds, then that makes it a little bit easier to read. Okay. And then yeah, there's a question about doing an overall normalization. You can do that as well. And typically, so, you know, you don't, so I guess I would say you don't actually have to normalize your data. The normalization process is really only to look at, and so these are good questions in the live chat. You don't have to normalize this. You can just have your counts, because the table that you calculate, we have this, let me go back up. So let me say, we normalize it to look at those trends, right? We can see those differences in the percentage of crimes that occurred in one place versus another. But you don't have to do that. You can have your count table, because if you remember, the way we calculated when we did this kind of by hand, or when we were going over the technique behind it, is that we made a count table, another count table for our null hypothesis. And then we say, how different is that count table for the null hypothesis? How different is that from our actual table? Where we had, you know, this count, which is raw counts, not percentages. And we made that other count table. And actually we can just, maybe I can find it. Maybe it would be easier just to talk about it on the actual lesson. Yeah, so where we had our actual, you know, count table here. Let me get back to, so then we made our fake, or our null hypothesis contingency table here. This is counts. We haven't normalized any of these. And then what we looked at was our chi-square test tested the difference between those two count tables. Okay, so the normalization process, you know, you can normalize it in different ways to look at it. And then you can also, there's a way here, if you didn't normalize it, if you just said normalize equals true, that will normalize the whole table for rows and columns. So there are different ways to do it, but chi-square is not calculated based off of normalization. It's based off of the difference in the actual counts of your data. So hopefully that clarifies a little bit. This is mostly for like this purpose, for you to see those trends and for you to share, for you to put those, to share them with others, right? When you are talking to someone about the trends you see in your data, it's important to actually demonstrate that to them, to show them your heat map, to say, we see these trends. But yeah, your chi-square is calculated off of counts. Okay, so the next thing that we can do is we can add a title. So when we're making our visualizations, we can, let me double check here. Okay, just checking the live chat really quick. Okay, and yeah, you can alter the color for heat maps as well. So if you wanted to add a title, what you would do is just, you would say this ax.set title. So in Seaborn, you use this ax so that you can use other pandas functions with incompatibility or like along with Seaborn. So this is just this, we want to take this, our heat map, we want to ax.set title. So what we named this here, we want to just take that function, our heat map, and we want to add a title to it. And so that's our title right here. And so that's a pretty simple way that we can add that description. And then again, here you can, if you view this, there are other things you can do to edit your heat maps as well, add more descriptions, specific visualizations. Okay, so let's also go ahead. So the next exercise, make a heat map of the normalized contingency table that you created in exercise 1. So let's go back. So we want to make a heat map. And remember, we made this contingency table in exercise 1 right here. Remember that we made this table here normalized by row. So what if we wanted to make a heat map of that normalized percentage contingency table? Go ahead and try to do the code. So remember, this was the code to make that original count contingency table. So then try to make that heat map of the normalized contingency table that we created in exercise 1. Okay, and I'm seeing already some really cool heat maps in the live chat. It looks like you're playing with the color schemes. That's awesome. And there are definitely, yeah, I see some purples, some yellows, blues, greens. So definitely a lot of options for your heat maps. Okay. So I know this isn't a whole lot of time for these, but like I said, I want to make sure that we can get through these, and I'm happy to come back if anyone is confused. But because hopefully this is pretty straightforward for exercise 2. So we're making that heat map. So it's the exact same code that we used for exercise 1. The only reason that it's printed here again is because we didn't give it a name. Well, maybe you did when you did exercise 1 on your own. But if we go back to exercise 1, do you see how we didn't name this? We didn't give it a variable name. So there was no way for us to call that heat map function. We had nothing to put in. We didn't have my contingency table. We didn't have a variable name. But it's this exact same code. So for exercise 2, it's this code, but this time we called it norm CT or norm count. So we gave it a name this time so that we could then say, use the Seaborn package, use heat map, sns.heatmap for the norm count. And we want it to be in the red color palette. And then we gave it a title, and that's .set title function. So again, the same code where we created this crosstab. We use this crosstab function to make a contingency table with the rows being offenses and the columns being location. We normalized it by row times 100 so that we could have our percentages, which just helps us with this table, because this is our key here for legibility. To say 60 means 60%. So if we see these darker, that's closer to 60%. So that's how we would make our heat map for our normalized table. Okay, so this next part is a little bit, hopefully not a little bit tricky. Hopefully you went over t-tests in the last lecture. But this is going to be how you can do those t-tests in Python using that Penguin package. So you were introduced to kind of hypothesis testing and t-tests. So t-tests are different from a chi-square test because t-tests are actually used to calculate the differences between, like, for example, the mean of samples, right? This is numerical data, it's not categorical data. So you use that t-test, I think in your last case, to calculate whether or not two different averages were statistically different. Is their difference statistically significant? So if you wanted to execute that in Python, it's pretty easy to run a t-test. It's 2 lines of code. So you can have a 1 sample t-test or a 2 sample t-test. So what we're going to do here is the first case is a 1 sample t-test. So what that means is, let's say we have taken from our, we're going to have this A data set, which is 244 values with a mean of 39.6. So that's what we have in our A CSV. So what we've done there is what we're saying for our t-test is we've taken the sampling, right? We have this data, we have 244 counts. And we're saying, is the mean of those 244 data points, is that statistically different from 56? That's a 1 sample t-test, right? Because we're just saying, is that sampling that we took, are those values, those 244 values, is the mean of those values from A statistically different from 56? So the way we do this is it's just 1 line of code, really. It's this, you use the Penguin package .t-test, and then we say this A, which is our series in the CSV, is that different from 56? So you could have put in any number here to see, is it different? And then our output is quite a few things. And so this is our T statistic, which is really just the difference in the normalized means. We have our degrees of freedom. It's 243 because our sample size is 244, and our degrees of freedom is our sample size -1. It's a 2-sided t-test, which means that when we do a 2-sided t-test, that means that we have given it the option to say that our mean could be above or below 56. We're testing it either way. Is it statistically different from 56, above or below? A 1-sided t-test you rarely will use because that only tests, like, is our mean above 56? So you're completely ignoring the possibility that our mean could be below 56. you're only taking into account one thing. You don't really need to know all of this. What's most important is your p-value. So the things you care about when you're doing a t-test are usually, mostly your p-value here. So these other values, are kind of less important. They get a little bit more statistically complicated. Like you have this Cohen D value, and that's your effect size. So if it's closer to 1, you have a larger effect size. If it's smaller, you have a smaller effect size, meaning that there isn't really a whole lot of difference. That it can all get complicated. So the main point here is that when you're doing your t-test, what we're testing is the mean of our A data set statistically different from 56? And so yes, it is. Our p-value is very, very small. And remember how we talked about that p-values are never 0. They can be very close to 0. This is pretty close to 0. This is 3.3 times 10 to the minus 30. So you're moving your decimal point 30 places up there. So it is pretty close to 0, which means it's pretty statistically significant. Your confidence interval says that you're 95% confident that your actual mean is between 37.11 and 42.03. And 56 is definitely outside of that confidence interval, right? So 56 is far away from 42. So we're pretty sure that our mean of our sample here, of our data set, is statistically different from 56. So this is how you would do that t-test. And then, so we can also do a two-sided t-test. Or sorry, a two-sample t-test. They're all two-sided t-tests. A two-sample t-test is that when you have two data sets where you have, you've taken multiple data points and you're trying to test the means of two different data sets. Okay, so here, remember, we did a one sample t-test where we had one sample. We had those 244 data points from A, and we wanted to know, is it different from 56? Here, we have two different data sets. We're now testing between A and between our B data set, which we loaded in here. So again, we do this penguin t-test to say, are these two means different? So in the comment, this is just some details to tell you that the mean for B is 37.15. And remember, we were told that the mean was 39.6 up here, just to save us some time so that we know. So, before we were looking at, is 39.6 statistically different from 56? Based off of our 244 samples. And yes, we decided it was statistically different. That those two, that mean is really different from 56. But here, that we can see that our p-value when we do this t-test is 0.195. So that's not statistically significant. If we used a p-value of 0.05 or 0.01, either way, this is above. So those two means are not statistically different from each other. You can also look at your confidence interval and see our confidence interval is from -1 to 6. And so we can see that not 100% sure what happened with this confidence interval. That doesn't make sense. Okay. I'm wondering if this printed this is the confidence interval and the difference between the means, maybe? It should have been the difference, and I guess that would be the difference. The confidence interval in this case is the difference between those two means. And so here we see that the difference between like 37.15 and 39.6, that difference is within this range of this confidence interval. And so we have this p-value that's not significant, so we cannot reject our null hypothesis. And Again, we have our degrees of freedom because we add up 215 and 244 and then subtract 1. You can also look at that Cohen value that I said was a little bit complicated, but you can also see up here it was 0.8, which meant that there was a pretty large effect size, that those were really quite different. Here you can see it's much smaller. Usually anything below 0.2 is a really small effect size and is not usually statistically significant, but sometimes can be. So yeah, our main thing to look at here is our p-value to say that these two means are not statistically different from each other. So let's try exercise 3. Conduct a 2-sample t-test between the A and C data sets. So we will go ahead and give you the code to import the C data set. So go ahead and do that 2-sample t-test, kind of like this, between the A and C data sets now. And there's a question, statistically significant means that the difference between those two means, or between that mean and 56, it was unlikely that that happened by chance, that was a random thing that could have occurred. So yeah, if it's statistically significant, it means that that is most likely a real relationship or a real pattern that you're observing, and that it's not something that happened by chance, most likely. And basically, I guess your p-value, like when you have a p-value of 0.05, what that's really saying is that there's a 5% chance that observation occurred randomly. So if you have a p-value of 0.04, you have a 4% chance that your observation, right? Let's say our p-value here, let's say was 0.04. Then you would say that there's a 4% chance that the difference between those means just would have happened randomly. And so that's a pretty small chance, right? So that's why there's debate about whether it should be 0.05 or 0.01, because that's saying, if you're at 0.01, you're saying there's a 1% chance that your observation occurred randomly. Some people think that 5% is too high, that could have been randomness. But here you're basically saying that there's a 19.5% chance that the difference in those means happened randomly. And that's pretty good. That could have been random. There's really not a difference between these two means. Okay. So let's go over our exercise 3. Because again, hopefully the code for all of these should be pretty straightforward, hopefully. I think the concepts that get a little bit complicated. So here we're doing, again, our 2-sample t-test, where we're just using this penguin.t-test, and then we're using our previous A data set that we loaded and C. We can see our p-value here is 0.0002. So that is significant. We can reject our null hypothesis. Our null hypothesis in this case is that the means are not different, right? No relationship or no difference. So our null hypothesis here is that the means of A and C are not different. But here we have a p-value that is significant, indicating that yes, the mean between A and C is actually different. They are statistically significant and statistically different from one another. Okay, so, and really, I know that there's a lot of different things that go on with the output. Really what you should look at when you're doing your t-test is that p-value. That's the most important thing to pay attention to. You don't have to dive deep into all those other, the output. You can, if you want to, you can certainly dive into that and learn a little more about that statistics. So the next thing that we want to do is our chi-square test. So we're going to change gears a little bit. We were talking about that t-test, which hopefully you covered more in your last lecture. But that's how you would do it. Very simple with that penguin package to test the difference between two means or one mean and a value. But now let's get back to our chi-square test. So if we wanted to do a chi-square test, if you remember in our last lecture, just previously, we talked about how you do it, where you make that counts table, and then we kind of calculated by hand almost our null hypothesis count table, where remember we multiplied probabilities, where we said the probability of one happening should be, multiplied by the probability of the other happening, and we made that null hypothesis count table. You don't have to do that by hand here. Actually, Python will do it for you, and it will just give you a p-value. So all you have to do is use this function chi2 contingency, and then you need to put in your contingency table. So remember, we named our counts table my contingency table. So we just do chi2 contingency, and then it will output a couple of different things. The most important is the second value. That's your p-value. I think this is the test statistic. This is your degrees of freedom, which is, it can be a little bit difficult to calculate. And then this actually outputs your table with, I believe that this is your actual expected counts table. So it will do this for you. If I'm remembering correctly, this is actually the table that has that if you had like a null hypothesis, what should the counts be? That's your expected. So what we care most about is, again, our p-value, because we inputted our counts table, and then we asked it to say, tell me if what we observe in our counts table is statistically significant. Is there a pattern? And so we did find out yes, because the p-value is very close to 0. That it is statistically significant. Now, this is a lot of output, right? It's giving you these things, that a lot of different numbers here, and this whole array of your null hypothesis table. But what if we just wanted to know the p-value, right? That's what we care most about. Is this a real relationship? Remember our crime in our locations. Is there a real relationship there? And so we can say that, yeah, we can just output this p-value by saying we just want the second value. Remember that Python counts things 0, 1, 2, 3. So if we wanted the second value, we would say a number 1. So we just use that chi2 contingency, and then we want to output the p-value. So let's try exercise 4. Okay, so this is a subset of the data set in which we only included the offenses that are violent crimes with locations in residential areas. So remember, we had that police officer who said, violent crimes happen everywhere. It doesn't matter the location, and we wanted to test that. So we've gone ahead and given you the code already for if you wanted to take a subset of your contingency table, or if you wanted to take a subset of your data set, we're going to call this subset df. And then we just want to pull out from our location column the residential and related, and we just want to pull out from the offenses column violence and related, anything that had those. And so that's what this outputs here is. This is the section of our data set that matched these categories. So now we want to make a contingency table of that location description versus primary type using this smaller data set. Remember, we named it subset df. So we want to make a contingency table using the smaller data set. So plot that as a heat map, and then report the p-value of the chi-square test. So basically do, using this subset data set, we want that p-value, a contingency table, and a heat map. So let's take just a minute. And there are a couple of questions about p-values and, oh, there's an explanation. Okay, so I guess you're going to cover p-values a little bit more in your next session. So that's awesome. And there was a question about, oh, overall. So when we get our overall p-value, that p-value equals 0, 0, which means it was really close to 0. That's overall. So that's not for a particular row or column. That basically says that it's basically everything. Is our whole table statistically, like, is our whole table statistically different from the null hypothesis table? Meaning, are those two categories that we compare in our row and column, is there a relationship between those two categories? And so yes, yes, there is. Okay, and so for the sake of time, I'm sorry, I always run out of time with you guys. I get too chatty and I always talk too much here. So let's talk about the answer for this contingency table. So what we wanted to do is, so we use the subset data frame. So we have, we're going to call this subset count. And so we just create our contingency table using crosstab. And then from our subset data frame, we are using that modified data frame. We want the location description and primary type. Those are the two things that we want to put in our contingency table, and then that outputs it. Remember, crosstab does all of that for you. And then if we wanted to make our heat map, we would say the same thing. We use this ax equals sns.heatmap, call our subset count in red, and then we want a title for it. So that's just giving us that the heat map here from this up above that we made our contingency table. We named it subset count. And remember, we got our data from right here, where we used that subset data frame, which pulled out only the residential and related crimes, and then violence and related crimes. And then the last thing that we wanted to do is we wanted to do that chi-square test. So all we have to do here is, if we just want the p-value, remember we use chi2 contingency, just this command here, our subset count, which remember that is from right here. We got that subset count where we made this counts contingency table. And so this also goes back to that normalizing. Remember, we didn't normalize anything here. That was only for visualization purposes. Here, we're just using our counts. And then we say we want just the p-value, so it'll output, and we wanted this in kind of a nice, easy to interpret way. So we said print p-value of chi-square test for primary type versus location. And so, it outputs that p-value there. So if we had just done this, it would have printed a 0, 0, which is fine too. So that just tells us that it is significant. So that's how, basically the takeaway here is that this is how you do those contingency tests to get that significance that we talked about in our last lecture. And then I'm pretty sure this is our final. Okay. So our final thing is that, remember how we talked about how we wanted to make time, we wanted to divide things by day. So remember we talked about how normally if you have numerical data, you can't do a chi-square test. We talked about that in terms of time, and we showed a heat map that looked at day for the type of crime. So the way that we would do that is, and I think all your answers also are going to be posted in polls and answers if you missed any of that code. But if we wanted to make this day, to make a contingency table with date. So what we would have to do for that is, from our original data frame, we have our date, we have a date column. We already have the date data. So what we're going to do is add a new column to our data frame called date reformatted. That's our new column. And then we do pandas.toDateTime, which we've gone over in the past and you've seen in other lectures. That's an easy command that tells Python the things in this date column. Those are make those into an actual date format that's recognized by Python. So that will put it in that new column called date reformatted, and it will output this. If we just print our date reformatted column, that's what it looks like. It's now recognized as a data type of date time. So we just use this to date time. Now we can use, since we've done that, we can use a lot of really cool functions from Python for that. So we're going to make a new column called day of the week. And then we just pull from our date reformatted column and we say .dt .day of week. So that's a command that actually pulls out, because now we've told Python these are dates, it now knows what Monday, Tuesday, Wednesday, Thursday, Friday is, and it will actually output for each one of our crimes what day it happened on. So our first 5 crimes happened on a Sunday. Oh yeah, so it actually told us Monday was 0, Sunday is 6. So the first couple crimes in our data frame, or in our data frame, happened on a Sunday. So this is how we can actually make that column that will just have the day of the week that that crime occurred. And then we can make our contingency table again. So we make our contingency table with this crosstab function using the offenses and then day of the week. And remember, we made our day of the week up here. So now we have that 0 through 6. And we have our offenses category. So since, for the sake of time, we're going to go ahead and I will show you exercise 5. So remember, our hypothesis in exercise 5 was to say, is there a relationship between day of the week and the type of crime? So the way that we would do that, actually for exercise 5, it's hour. Okay, so we're going to look at whether the time of day is related to the type of crime. So, this is very similar to what we did in the last one, where instead of using dt.day of the week, we use dt.hour to pull out the hour that the crime occurred. And then we again can make our contingency table with hour of day and the location. So I know I'm going kind of quick through this part, but this is all repeating code. So hopefully after this lecture, you can all go back and kind of look at this code. Since we've already gone through what crosstab means, what the chi2 contingency means, this is just different applications of it. So hopefully, this isn't too complicated code. These are just different ways you can do it. So you can always use this as a reference. So here we're making a heat map of that hour of the day versus, location, or you could have done type of crime. We make our title, so it's still using that heat map function. And then again, we just use our chi2 contingency. So I know I went really fast through this last part here, but again, I encourage you to reference this. It's just we're using the same commands over and over. So that this chi2 contingency is how you do your actual test, your contingency test, that will tell you, or your chi-square test, that will tell you if your contingency table, if your values, if there is an actual pattern, if it differs from your null hypothesis. Your crosstab makes your contingency table, and then the heat map function is really helpful for showing you if there are those patterns that arise. So yeah, this was kind of fast, and I apologize at the end for that, but it sounds like you're going to have another workshop on hypothesis testing next. So hopefully that will clarify any questions that you have, and hopefully you can use this in your projects. This is a really, really helpful statistical test for comparing 2 or more categorical variables. So yeah, that is all for me. Thank you so much. And I hope that this was a good lecture. I hope you all learned a lot. And I look forward to seeing you in the future.
Thank you so much, Sarah. We know it's a difficult topic for some, but don't worry. As Sarah said, we are going to have a type of lecture with one of our best TAs in the